Welcome to sub-module 1 of 3 on hole cleaning. In this session, we will introduce the fundamentals of hole cleaning, its importance in efficient drilling, and set the foundation for the next two modules, where we'll explore detailed mechanisms and optimization practices. In this sub-module, our primary objective is to understand the key factors that influence hole cleaning and how to optimize these for efficient drilling operations. Hole cleaning is essential to maintaining wellbore stability, ensuring smooth drilling progress, and preventing costly problems such as stuck pipe or excessive torque and drag. We will begin by examining the well profile, which defines the geometry and inclination of the borehole. The shape and angle of the well directly affect how cuttings move, making it more challenging in deviated or horizontal wells compared to vertical wells. Next, we will consider the flow profile and parameters. These include annular velocity, mud circulation, and turbulence, all of which play a critical role in lifting and transporting cuttings effectively to the surface. We will also cover mud properties, since density, viscosity, and gel strength determine how well the drilling fluid suspends and transports cuttings. Another important factor is pipe movement, as drill string rotation and reciprocation can enhance hole cleaning by disturbing cuttings beds. Finally, we will look at cuttings bed removal, focusing on strategies to minimize accumulation and maintain efficient transport. Together, these elements form the basis of effective hole cleaning practices. For this course, we will focus on the fundamental elements that influence hole cleaning. The first is the well profile. A vertical well typically provides efficient cuttings transport because gravity assists removal. However, as inclination increases, especially beyond 35 degrees, cuttings tend to settle on the low side of the hole, leading to bed formation. Horizontal wells represent the greatest challenge, often requiring enhanced circulation and drill string movement. The second element is the flow profile and parameters. The annular velocity, or speed of fluid moving up the annulus, must be sufficient to exceed the slip velocity of cuttings. Turbulent flow improves suspension, whereas laminar flow increases the risk of cuttings settling. Optimizing flow rate and rheology is therefore critical. The third element is mud properties. Density provides hydrostatic support, while viscosity and gel strength help suspend and transport solids. Thixotropic properties are particularly important during pump-off periods, preventing excessive cuttings from falling back. Next, we consider pipe movement. Drill string rotation and reciprocation disturb settled beds and increase turbulence, particularly in deviated wells. This mechanical assistance is often necessary when circulation alone is insufficient. Finally, cuttings bed removal must be actively managed. If neglected, accumulation leads to increased torque, drag, and risks of stuck pipe, severely impacting drilling efficiency. The pictures on the right highlight the key elements influencing hole cleaning. The first image shows the well profile, reminding us that inclination affects cuttings transport. Vertical wells are easier to clean than horizontal ones. The second image below and to the left illustrates flow profiles, where turbulent flow suspends cuttings more effectively than laminar flow. The third image below and to the right demonstrates the boycott effect, where cuttings settle and slide to the low side of deviated wells, forming beds that hinder cleaning. Finally, the fourth image at the bottom shows how pipe movement disturbs settled beds, enhancing transport. This picture illustrates cuttings transport in a vertical wellbore. The drill pipe is positioned centrally within the hole, while circulating drilling fluid moves cuttings upward in the annulus. The arrows represent annular velocity, Vn, which is the fluid velocity carrying cuttings toward the surface. The key concept is the relationship between annular velocity and the slip velocity of cuttings, known as V-slip. Cuttings naturally tend to fall under gravity, and this downward movement is defined as slip velocity. The effective transport velocity is expressed as V-transport equals Vn minus V-slip. If annular velocity is greater than slip velocity, Cuttings are transported effectively to surface. If not, they settle back toward the bit. Hole cleaning efficiency in vertical wells can be defined as the ratio of transport velocity to annular velocity. Hole cleaning efficiency equals V transport divided by V an. Vertical wells are typically the easiest to clean, since flow is symmetrical around the drill pipe and gravity assists upward transport. The key takeaway is that in a vertical hole, flow dominates for hole cleaning. Now let's look at settling velocity. This is defined by Stokes' law, which explains how particles settle through a fluid. Let's work through the terms. Vs is the settling velocity, basically how fast cuttings fall. G is gravity pulling the cuttings down. dc is the particle diameter. The larger the cutting, the faster it falls. Rho c is the density of the cutting itself. Rho f is the density of the fluid. The closer these are, the slower the cuttings drop. This law was developed by Sir George Stokes, a 19th century mathematician and physicist who pioneered the field of fluid dynamics. His work still underpins how we model cutting transport today. In drilling, the takeaway is simple. Big, dense cuttings in thin mud will settle quickly, risking bed formation. But by increasing mud density or viscosity, we reduce slip velocity and improve hole cleaning. It's all about finding the right balance. Now let's look at the effect of particle slip with deviation. How does wellbore deviation affect the way particles, or cuttings, settle in the annulus? We see three images from left to right, representing three inclination ranges. In the first image, range 1 covers 0 degrees to 35 degrees deviation. Here, particle slip is mainly axial, meaning cuttings tend to fall directly downwards, assisted by gravity. Transport efficiency is relatively good, and cuttings are readily carried by annular flow. In the second image, range 2 represents 35 degrees to 55 degrees deviation. At this intermediate angle, slip becomes a mix of axial and radial. Cuttings begin to migrate toward the low side of the borehole. This is the most critical range because cuttings beds form rapidly, while annular flow is not yet fully effective in resuspending them. Hole cleaning difficulties are greatest here. The third image shows range 3 from 55 degrees to 90 degrees deviation. In this zone, slip is predominantly radial, meaning cuttings slide sideways toward the low side of the hole, forming continuous beds. In horizontal sections, removal relies heavily on high annular velocity and drill string movement, since gravity no longer supports upward transport. The key learning is that inclination strongly influences slip behavior, with range 2 being the most problematic for hole cleaning. Looking at the critical transport comparison, or how cuttings transport changes with wellbore inclination. The graph compares three mechanisms: rolling, lifting, and settling of particles in the annulus. Along the x-axis, we have wellbore angle, from vertical at 0 degrees to horizontal at 90 degrees. On the y-axis, we see mud velocity and flow rate. In a vertical hole, the drilling fluid easily suspends cuttings, and relatively lower annular velocities are sufficient to transport them to surface. As we move into the intermediate angle range, between 35 and 55 degrees, transport becomes most critical. This is where cuttings tend to both roll and settle on the low side of the hole. Rolling is a process where cuttings roll over each other in a wave-like motion. The flow regime is less effective at lifting them, so higher annular velocities are required to avoid cuttings bed formation. This is the most challenging range for hole cleaning. Finally, in high angle and horizontal well, rolling becomes the primary mode of transport. The fluid struggles to lift particles effectively, and cuttings continuously migrate to the low side. In these cases, we rely not only on velocity, but also on mechanical agitation, such as drill string rotation and reciprocation, to disturb beds and keep the hole clean. The key message, hole inclination, directly controls cleaning efficiency, and hydraulics must be designed accordingly. The graph shows how hole cleaning difficulty increases with inclination. On the x-axis we have well inclination, from vertical at 0 degrees to horizontal at 90. On the y-axis we have the relative difficulty of hole cleaning. In the low inclination range up to about 30 degrees, hole cleaning is relatively straightforward because cuttings are lifted axially with the fluid. In the intermediate range, around 35 to 55 degrees, difficulty increases sharply. This is where the boycott effect comes into play. Cuttings no longer move purely upward, but begin sliding toward the low side, forming beds. This is the most problematic range for hole cleaning. As the hole becomes highly deviated or horizontal from 55 to 90 degrees, difficulty levels off but remains high. Here, cuttings transport relies primarily on rolling along the low side of the borehole. Without pipe rotation or reciprocation, these cuttings can quickly form stable beds. The key takeaway is that the greatest challenge lies in the intermediate build section, where both axial and radial slip compete, making cuttings removal least efficient. When talking about solids settling, we need to understand boycott settling in a deviated well. Instead of cuttings simply falling through the fluid, the inclination causes particles to migrate sideways to the low side of the hole, where they rapidly form a cuttings bed. Visually, note 3 zones. At the top, the fluid is clarified. Most solids have already moved out of this region. In the middle, a suspension zone carries dispersed particles. Here, fluid, rheology and shear partly support the cuttings, but not enough to prevent lateral migration. Along the bottom, a sag sediment bed accumulates on the low side. When pumps slow or stop, that bed can slump, thickening and becoming harder to re-entrain. This effect is most pronounced in the build section. As inclination increases, the gravity vector has a stronger radial component, so particles slide faster toward the low side. Practically, that means even with adequate annular velocity, you can still see bed growth, rising torque and drag, and eventual packing off. Mitigation focuses on reducing the effective slip advantage, increase annular velocity, tailor rheology, sufficient yield point to support particles without excessive ECD, and add mechanical agitation, rotation and reciprocation to break and re-entrain beds. Periodic sweeps and short conditioning circulations in the build are especially effective. Okay, let's continue with solid settling. Here we are focusing on slippage and cutting bed formation. When we say slippage cancels the vertical component of mud velocity, we mean that the natural downward slip velocity of the particles directly offsets the upward annular velocity of the mud. When those two forces balance, the cuttings stop moving uphole and begin to accumulate in the annulus. That leads us to the next point. Cuttings build up until equilibrium is established. Once this balance occurs, a bed forms at the low side of the borehole. These beds compact quickly, and once they're in place, it becomes increasingly difficult to erode or re-entrain them, even if you increase flow rate. From an operational standpoint, we need to evaluate solids build-up on connections. A reliable indicator is a rise in torque and drag after a connection or while sliding. If these values climb, it's often because cuttings have slumped into the borehole. That term slumping refers to cuttings beds collapsing downward when pumps are slowed or circulation is stopped. These slumps can rapidly reduce hole clearance and may lead to pack-off. Finally, the slide draws a comparison with turbidites, geological deposits that form in layers and harden over time. The analogy is clear. Once a cuttings bed stabilizes, it behaves just like a sedimentary deposit and resists removal. The key takeaway is that slippage is a self-limiting condition. If not managed with the right hydraulics, mud properties and drill string movement, cuttings beds will inevitably form. Now, let's look at the three primary flow regimes in drilling fluids: turbulent, laminar and plug flow, and their impact on hole cleaning. Starting with turbulent flow, in this regime, the fluid motion is chaotic, with eddies and vortices mixing the entire annulus. This is the most effective regime for cuttings transport because turbulence suspends solids and minimizes particle slip. However, the trade-off is higher pressure losses, which can lead to elevated equivalent circulating density. That increases the risk of fracturing the formation, and turbulent velocities can also cause erosion along the wellbore wall. Next is laminar flow. Here the fluid moves in smooth layers. Velocity is highest in the center of the annulus and falls to zero at the wellbore wall. While laminar flow is stable and produces lower pressure losses, it performs poorly for hole cleaning. Solids tend to settle against the low side, particularly in deviated or horizontal wells, making cuttings beds and pack-off more likely. Finally, plug flow. In this case, most of the fluid moves at nearly uniform velocity, but velocity at the wall is close to zero. This can help stabilize transport in eccentric annuli, but the stagnant boundary layer still allows cuttings accumulation. The key message here: effective hole cleaning requires controlled turbulence, enough velocity to suspend cuttings, but not so much that we create excessive ECD or erosion. In this sub-module, we have explored the key elements of hole cleaning and how to optimize them for efficient drilling operations. We began with the fundamentals: the influence of well profile, flow parameters, mud properties, pipe movement, and cuttings bed removal. We then examined cuttings transport in vertical wells, where efficiency depends on the balance between annular velocity and slip velocity, defined as V transport equals Vn minus V slip. Using Stokes' law, we introduced the parameters affecting particle settling velocity, highlighting the importance of mud density, viscosity, and particle size. Next, we reviewed the effect of deviation on particle slip, showing that hole inclination significantly alters transport, with the 35 to 55 degree range being the most problematic. The critical transport comparison reinforced this, illustrating the shift from lifting in vertical wells to rolling and settling in horizontal sections. We also looked at solid settling, focusing on the boycott effect, where inclination accelerates cuttings bed formation, especially in the build section. We related this to operational indicators such as torque and drag, as well as geological analogies like turbidites. Finally, we compared flow regimes, emphasizing that controlled turbulence provides the most effective hole cleaning while balancing erosion risks and ECD management. This concludes the first submodule, 1 of 3 on hole cleaning. Please proceed to the quiz. Thank you.